Okay, in this video I'm going to do a short introduction on how to create offline programs to be run on robotic devices. And by offline programs, I mean using a particular software to generate a program, a script, that then can be loaded manually into a robotic device and then can be run once or can be run in cycles. The difference between offline and online is that in offline the program is generated a priori and then it's loaded into and is loaded and executed. And online is that there is a direct connection and data transfer between a client, so for example a laptop, and the robot. So in this tutorial we're going to look at offline, aka creating the program beforehand and then running it on the computer. I'm going to use Machina, which is a framework for controlling robotic devices. And specifically what I'm going to do is I'm going to use Machina for Grasshopper, which is a visual programming language that works for Rhino and the 3D modeling software. What you can see is that what I have here is Rhino, the modeling environment, and I have Grasshopper, which is the generative, the parametric design environment for Rhino. In this one, I have all the typical components and the menus, and I have downloaded and installed Machina for Grasshopper. If you have any questions on how to install Machina, you can go to the main repository of Machina for Grasshopper, and here there is instructions on how to install it. But also, probably one of the best ways of doing this is going to Food for Rhino. And in Food for Rhino, just Googling Machina. And then here, you should always have access to the latest version of this download with the most updated features. So in this video, I'm currently running version 0.5, but maybe version has been updated when you watch this video. Actually, for example, these links are outdated. So anyway, going back here, from the Machina menu, you can see that basically the main category of components that we have available is what's called actions, because any Machina program is simply and just a list of actions one after the other, and actions being a particular instruction that you want to tell the robot to do. So for example, you can tell the robot to move somewhere, you can tell the robot to rotate around an axis, you can tell the robot to transform to a position. This includes motion, but it also includes reorientation. You can set the speed of the movement, you can set the precision of the movement, you can wait for a specified amount of time, you can create messages that will pop up on the robot controller, and you can attach detach tools and work with the IOs, the digital pins or the analog pins of a particular device. If instead you're working with 3D printers, you can also do some extrusion operations and control temperature of devices, etc. Right? So this is basically it. And if you hover over the instructions, you can see notes and you can see comments on what each one of these actions does. So in order to create a program with Machina, it's just as simple as writing a sorted list of all the actions that you want the robot to execute one after the other. Okay, so very simple. So what we're going to start doing here in this sample is I'm going to create, I also have Robot Studio running here with me, which is going to be the simulation environment that I'm going to use to simulate the programs that I'm going to be creating. And if you don't know how to install or set up Robot Studio, you can check my other videos on how to do this. So this is the robot that is going to be, is sort of in a home position. So all the axes are at 0 rotation except for axis number 5. So what I'm going to do is I'm going to create a super simple program that is going to make the robot move in a straight motion, in linear motion, from a point somewhere here in the air, so in this quadrant here, linearly into some other point which is going to be somewhere in this quadrant here. So as you can see, the coordinate system of the robot is this one, and it's centered at the base of the robot. So if you were to move this here to this center, then the x-axis will be positive here, the y-axis will be positive here, and the z-axis will be positive here. We also need to keep in mind that whenever we tell the robot to move to a particular orientation in space, like for example a plane, the orientation is going to be according to what's called the TCP of the robot, or the tool center point. So as you can see, the coordinate system of the TCP right now is similar to the global one, except for a 180-degree rotation around the y-axis. So you can see that the y-axis is the same, but both the z-axis and the x-axis are inverted. The z-axis is pointing down and the x-axis is pointing inwards. So this is something we will need to keep in mind when, for example, we design planes that make the robot move to a particular rotation in space. Okay, so if the first thing that we want the robot to do is to move to somewhere in this quadrant, then if we look at the list of actions that we have available, probably moving is the one that we want to choose. So I'm going to drop this here, and if I zoom into this component, we can see that it takes a point as an input, the target point that we want to move to, and it returns a move action, right? And we can also see that this action is set to be in absolute coordinates, which I will get to back what this means in a second, okay? So very simple. What we're going to do is we're going to give it a point, and then we're going to make sure that we're going to give it a point. So I'm going to create a new point here, and this point is going to be like this, and I'm going to give some coordinates here. So for example, I'm going to say I want the robot to to move to x coordinate 300. I want y coordinate to be negative in this case because I want the left hand side. So I'm going to set this value to be minus 400, for example. And then the z height is going to be somewhere, for example, 200. Okay. So if I zoom out, I can see that according to the orientation of the robot, which is more similar here now, I can see that the point is in this quadrant, right? And I have created an action to move to this point. If I plug in a panel to this action, I can see a human representation of what this action means, so moving to this coordinate in space, right? Well, that's great. If that's the case, then if I wanted the robot to move linearly from this point to another point in this positive XY quadrant, then probably what I need to do is I need to create another action that is also moving, but it takes me to that other point. So that point can be the same coordinates, but just at positive 400 in the Y direction. And then I can plug this in here, and I can see that, yep, this is another move instruction. So that's pretty much it. I can now create a program based on these two simple actions by doing the following. I can just go to sets, and I can combine all these actions into a list. So for example, I can do this, and I can see that if I stream my program to human reader to a panel, this is what the program is going to look like. Move to these coordinates and then move to these other coordinates. Awesome. So if I have that, the only thing that I need to do now is I need to compile this program into whichever native language that program is going to run. Okay. So how can I do that? Well, you see that the compilation component takes a robot as an input, which means first I need to create a representation of the robot that is going to run this program, right? So for that, I can come here to new robot, and then I can give the robot a name. So for example, straight line test. And then I can tell the robot what kind of brand is going to be running this. And this is important because the robot needs to know, the compiler needs to know the brand of the robot so that it chooses the right language to compile to. The next that we want to choose is going to be actions. So actions is just the program as a list of actions, one after the other, which are going to be what's going to be compiled. And that's pretty much it. Then the next thing you can do is you can plug a panel to the compilation, and you can see that we have just generated a program that in ABB language that contains all the necessary instructions to run those actions. So is that true? Let's give it a shot. So what I'm going to do is I'm going to choose the destination for copy pasting this program. So I'm going to say, for example, this is going to be I'm going to compile to a file called straightline.prg, because PRG is the file extension for programs in ABB robots. And then I'm going to choose to stream those contents to that file. Because I chose my desktop, I can go to my desktop now, and I can see that the file straightline.prg, if I open it up with a text editor, so for example I'm using Atom, which is is a free text editor that you can download for free, and it's very convenient for code. I also have this module that allows me to do syntax highlighting for rapid code. I can see that I have exported this simple program that contains 2 instructions, and I can see in the comments what each one of those instructions corresponds to. So I think we're ready to try this on the robot, which is something that you should always do before trying things in a real physical device. You should always try to simulate them beforehand. So I can go to Robot Studio, and in my Rapid tab in my robot, I can right-click on the T-Robot task. I can load a program. First, I can choose the old PRG format, go to the desktop, and then look for straightline.prg. As I load this program, I can see that there were no errors, everything was fine. And if I hit start, you can see that the robot is slowly approaching this point in space that we set. And once it reaches that point, it will start moving to the other point linearly. Why is the robot moving so slowly? Well, it so happens that by default, if we don't tell otherwise, Machina designs programs at a very low speed for safety reasons. So, but you can see how it's getting very close to 300, minus 400, and 200, which was the first point that we told it to. And as soon as it reaches that target, wait for it. Well, it is really slow. So we're almost there. You're going to see that it's going to start moving this way, and it's now starting to move this way. Exactly. So obviously this is too slow, and we probably don't want to do that. So something we can do is that we can increase the speed of the movement before we start the program. So I'm going to stop this program, and I'm going to modify this program to increase the speed at which it should execute. So where am I going to do this? Well, the first thing I'm going to do is I'm going to drop a speed component, which is going to set the speed at which future actions will be executed. And then I'm going to set it to a value, for example, of 150 millimeters per second, right? And then what I'm going to do is I'm going to plug that action in the program before executing any other of the 2 actions. So you can see that my program now looks set the speed to 150 and then move and move. The exported program looks very similar. And if I go to Atom right now, you can see that my straightline PRG file has updated with the new speed value. So if I reload this program into my simulation environment, so I go right click, load program, yes, I want to override the program. I want to override the program, and then I look for my sorry, I need to set this to PRG. If I look for my program, you can see that it just loaded it, and if I hit start, it's going to start moving to this first point right away, quite faster than it was before. So it's going to start, and it's much faster now. You can see it reached that point, and then it's going to start moving towards the second point. But as it does, you can see that it stopped before reaching that point, because what you can see is that it gave me a joint out of range error. It means one of the joints, joint number 3, is out of working range. I can see that also in the joint jogger, that joint number 3 is very close to its limit. And I can also see that visually by moving this around and seeing that the robot is kind of like very bent into its own side. So it looks like this trajectory, it's too close to the robot, and the robot cannot execute it. So, well, that's not a problem, because we're doing parametric design, which means we can rework the numbers and create a new program very fast. Okay, so let's do that. So I'm going to go back to Grasshopper, and then I'm going to rework these numbers, and I'm going to push these 2 points farther away from the robot, which means I'm going to increase the x coordinate of these 2 points, right? And if I wanted to be a bit more parametric, I could just basically plug these 2 guys in, and then you see that everything updated here, everything updated here, everything updated in Atom. You can see the coordinates of my points have updated, and then I can probably load this in Robot Studio now and run it much faster. So I'm going to set PRG straight line. I'm going to load this, and I'm going to execute my program. It's getting farther away, and then you see that the robot got to that point and is moving farther down into this. And because my motion is set to continuous, it's looping through the program back and forth. So I can set single cycle so that my program executes once, and then when it reaches this other point, it will stop. And it just stopped, and you can see that everything turned off. Great, so that's awesome, it's working. Something that you may have noticed is that I have kind of hard-coded the coordinates of both points, and that I had to manually move one or the other, right? When I have to change them. So something that's interesting about the way Machina is designed is that this was such because the actions that I created were taking input in absolute coordinates. So they were taking the locations of the points in absolute coordinates. But I can actually rework or redefine the same action. Instead of in absolute coordinates, I can redefine it in relative coordinates, so that my program can be moved to this point, and whatever this point is, just move a particular amount, a particular distance in this direction. So let me do that. Let me do that here. So what I'm going to do is I'm going to right click on this option, and instead of absolute, I'm going to turn it into a relative motion. And what you can see is that now my component, instead of asking for a point for the motion, is asking for a vector. It's asking for a direction in which to move. So this action is not anymore in absolute coordinates, but it's in relative motion. So what I can do then is I can just feed it a vector. So for example, what we're going to do is we're going to move from here in this direction 200 units. So that's going to be in the positive y direction and 200 units here. And if I gave it this vector, now the whole program is working fine again. And you can see that the human representation of this program is set the speed, move to this location, and then move in this direction. If I run the compiled program like that, I'm going to load the program, I'm going to set PRG, and I'm going to look for a straight line. Let's see. I can go, and it's going to go to the first point, and then it's going to move 200 units in the y direction, and that's it. So that's the difference between absolute coordinates and relative actions. Absolute actions and relative actions. Before we move on into looking at other examples, I would like to add a couple more features to this simple program that we just created. Where, for example, right now what's happening is that the robot is moving to this one point and is moving 200 units in this direction, okay? But if this was some kind of real-world application, such as having the robot draw with a Sharpie on a paper, we may want to fine-tune some of these aspects. So, for example, we may want the movement of getting close to the paper, to the first point, to be very fast, but then we may want the movement of drawing the line to be much slower than it is, than the approach velocity. And also, something that we may want to do is, and that is also very good practice, is once you have finished executing your program, it's good practice to move the robot back to a home position, to a relaxed position. So that's kind of what we're going to do right now. So the first thing is we set up the speed to be very fast, like 150. We're actually going to do it a bit faster, right? And then we move to the first starting point. So I'm going to group this as and I'm going to call this the approach moment, okay? So after that, something that we can do is we can slow down. I think I set this to 250. We can slow down and we can draw with this virtual Sharpie at a much slower speed. And then something that we may want to do is we may want to make this movement very precise. So for example, we may want to increase the precision at which this movement is going to happen. And we can do that by, for example, setting the radius of that motion to 1 millimeter. That means, the radius means that the smoothing that's going to happen between targets is going to be of a radius of 1 millimeter. So that can be our second group of actions. So that's going to be drawing this virtual line, for example. And then we can plug them in order into the list. So we're going to set the speed, we're going to set the precision, and then we're going to move 200 units in the Y direction. And then after that, something that we may want to do is we may want to move the robot back to a relaxed position, to a home position. Since we're not really clear what the actual XYZ coordinates are, we may estimate them, and that's a good thing to do. But instead of that, we can use the axis component to set manually the angular rotation of each one of the joints of the robot. And I can tell you, for example, that for ABB robots, it's usually this position that we have here, this one, would be all the angles at 0 degrees, except for axis number 5, which would be at 90 degrees. So something we can do is I can just write a panel here and say these are all going to be at 0 degrees, this one, except for axis number 5, which is going to be at 90 degrees. Right? So that's also an action that says set rotations to 0, 0, 0, 90, and 0. But on top of that, we probably want to, when we go back home, we probably want to increase the speed again. So we can do 250, or we can do 250 here, or we can just copy the same velocity that we used for the previous action. So I'm going to now here group this as go back home, and I'm going to plug the speed and the action into the program. It's very important to remember that actions that change settings, such as for example speed or precision, they must be executed before the actions that they want to change. Because what this means is that whenever I set the velocity of the robot to be 250 millimeters per second, any action that happens after I set this speed is going to run at this velocity. And if I override this with a different value, then any action in the program after I set the new speed is going to be executed at this new speed. So that's a core principle between what's called state-based programming of the robot. If you set the state of the speed, then any action after that state has been set is going to be executed with those values. So this is what our final program looks like. We set the speed to a high value, we move to these coordinates, we load down the speed, we set the position, and then we move relative to the last coordinate, 200 millimeters in the y direction, and then we set the speed back to very fast, and we set the joint rotations of the robot to 0, 0, 0, 90, and 0 degrees. If we compile this to rapid code, this is going to be what our program is going to look like. If we look at that program in Atom, now it updated, and this is what the rapid code looks like. And then if we load that into Robot Studio, I'm going to load this program, and I'm going to set straight line. This is going to be the case, and I'm going to run this. So it's going to go very fast to that point, then very slowly at 50 millimeters per second, executes, draws this 200 millimeter line, and then it goes back to home position and stops. Because it's at home position now, it's a good moment to start the program again. It moves to the first coordinate point, and then it draws the line 200 millimeters, and then it goes back to home position. Something we could do is maybe when we start the line and when we stop the line, we could make the robot wait a small fraction. So for example, we can make the robot here wait 1000 milliseconds, which is 1 second, right? And we can plug that in between the first motion and the second motion, and we can copy paste this and then just plug it in here before going back home. As we do that, then our program gets updated, then this new program is compiled. If we look at Atom, we now have 2 wait instructions in between, and if we simulate this, if we load the new program and we simulate it, then you're going to see that it moves to the first target point, it waits for 1 second, and then it starts moving 200 millimeters, is going to wait for another full second, and then after that it's going to go back home. There you go. So that is the way you program robots offline in a nutshell with Machina. So for the things you can do to improve, you can just try things. So you can just drop components and read their descriptions and then figure out what that means based on those helpers. Something that is very helpful as well is that with your download of Machina, there's a set of sample files that you can read that help you through many things that you can do. So for example, there are examples for following a toolpath, doing some tool changes like milling a surface, doing some 3D printing. For example, if I open this one that is called vertical square, so you can see how programs are just created by, like we saw before, just compiling a bunch of actions one after the other, right? And then here I'm setting the speed to a value, I'm setting the position, I'm setting motion to be a joint motion instead of linear. It's a type of motion that is a bit more organic and natural to the robot, but that creates somehow unpredicted results. So it's not a linear motion in Euclidean space. So we'll only use this motion if you know that the robot is not going to be around obstacles and it's not going to hit anything. Then you can move to the base point. You can rotate the robot flange relative to its current position, minus 90 degrees around the y vector. Then wait a little bit, then draw a square, based on relative actions, then wait another point, and then just go back home. So if these parts of the program are compiled into a larger program which reads like this, setting the motion, precision, move to a point, rotate, and then draw the square with 4 relative actions, and then go back home. If we run this program that has been created for ABB robots, we can see that I can stream this content to Square. I just sent this to the desktop. I may have to set .prg exactly, and I'm going to stream out those contents. And now if I go to Robot Studio, I can load that program by going to the desktop, setting PRG, setting Square, and let's see if this works. So the robot is going to move to the first target point. It's going to move to the first target point, and then it's going to rotate 90 degrees down. Then it's going to move and trace a square of 75 units, and then it's going back home. So that sounds great. Something interesting about Machina is that for example, when you compile, you can choose whether if you want to have in the program, whether if you want to have comments that display what is going on in the program at any time. So if I turn this on, you can see that my program extends to add some comments here that define where and when I'm setting different values for the speed and the motion. It also adds comments to motion related. So for example, this line means it's moving. This line means it's rotating. I can, instead of having certain values be inline, for example, the locations or the rotations, I can set those as global variables, and then the movement is going to refer to those variables. Depending on what we're doing and the intensity of the computation that the robot is going to need, this may or may not be more convenient. But more interestingly, because the language that Machina uses is generic and is agnostic to the device that it's running, if I just happen to say and to define that this robot is not an ABB, but instead is a universal robot, then the program just compiles to universal robot. So, sorry, it just compiles to UR script, which is the universal robot language. Or if we define that it wants to run on a KUKA, then now this program has been compiled to KUKA PRC language. It also even works for 3D printers. So right now the only post-processor is CMorph, but you can see that the program has now been exported to G-code. So potentially you could 3D print as well with this rig. So yep, that's it. You are welcome to check more of the examples that are contained with the plugin, and then learn how to do different things with offline programming for the robots. Something else that you may want to try is using Machina in Dynamo BIM. The API, the interface, and the logics are the exact same as they are in Grasshopper, and they're also the same as they are in the core library, the C# library that runs behind these visual programming languages. So the way to install Machina for Dynamo is by going to the package manager. So you can just go to packages and search for the package that you want to install. And then here, if you type Machina, you should be able to see here Machina and then you should be able to see a drop down of all the different versions that have been published. You should always just try to install the latest version probably. And then once you do, and then you open a new file, you will see that you will have here a drop down with the same API of actions that we had in Grasshopper, except that these ones are divided in the relative one, precision, and the absolute one, precision 2, or the relative one, move, and the absolute one, move 2. But everything else is the exact same thing. You can also navigate to you can also navigate to where the folder that contains the plugin. So here in Machina, you can go to manage packages and show root directory. And in here, you will see that there's an extra folder that contains examples, the same set of examples written in Dynamo. So for example, if I open this file in Dynamo, you can see that I have created the exact same program. I'm setting the speed, I'm setting the position, I'm setting the motion mode, I'm moving the robot, and then I just created the same program. I can see the human representation of this program, and here I'm also with a new robot that is of an ABB. I'm also compiling the same program to native code in rapid language, and then I am exporting that program to this PRG file here. This is a PRG file that I could load into Robot Studio, and I could just run it. And then it would trace this vertical square here. So same thing, you're welcome to use one or the other, whichever you feel more comfortable with.